Well, welcome everybody. Thank you so much for joining us today. My name is Katherine Spector. I'm a research scholar at the Center on Global Energy Policy here at Columbia. And tonight we're going to be talking about the IEA's new report, The Future of Petrochemicals, with its co-lead author, Peter Levi, who I will introduce in just a moment. Let me quickly say that this event, like all of those at the center, is being webcast live, and both the full video and a podcast recording will be available on our website and on iTunes in the next couple of days. And for those of you watching online, as well as people here in the audience, you can ask a question for the panelists at any time using the hashtag CGEP events and our Twitter handle @ColumbiaU Energy. So keep that in mind. I just want to say a few words as well about tonight's topic. This study explores the role of petrochemicals in global energy today and also looks ahead to the future at the growing role that petrochemicals will play in oil and gas markets, in global energy security, and in many of the environmental themes that people are talking about today. And I have to say this report is incredibly useful and also well-timed. This is a topic that many of us are grappling with now. And here at the center, one of the things we're working on is an analysis of long-term oil demand. And petrochemicals are obviously a very key part of that. I was particularly struck by the fact that last year we took a look at all the other studies out there on long-term oil demand, and all those studies really did emphasize petrochemicals as the biggest source of oil demand growth in the future. But at least in the publicly available materials, none of them really got into why or had a whole lot of discussion about the rationale for that. And I found that striking. And it seemed to be, as Peter terms it, a real blind spot for the industry. And as I started to look into the petchem sector myself, I started to realize why. It's because it's just very, very difficult, I think. And for that reason, we're really happy that IEA has spent the time and effort on this report. Just to give one example, the expected shift to alternative passenger vehicles, whether it's electric vehicles, automated vehicles, is expected to reduce gasoline demand going forward, which should free up some light end material for naphtha production, which is, of course, one of the primary feedstocks for petrochemicals. At the same time, the expectation is that these new types of vehicles will be constructed with a lot more plastic, which will in turn increase demand for petrochemicals. So there are a lot of interesting interactions and feedback loops like that make it very difficult, in addition to the fact that even I think by energy market standards, the challenges presented by the availability and quality of data in this sector are really a very big challenge. And so this report does a tremendous service, I think, to the energy community by not only compiling and analyzing a really impressive collection of data on this topic, but also mapping out many of these complexities and trying to make sense of them. I want to just introduce our speakers. Peter is an energy analyst in the Energy Technology and Policy Division of the International Energy Agency, or the IEA. He focuses on analyzing energy-intensive industries, particularly the chemical and petrochemical sectors, but also on other cross-cutting themes with respect to decarbonization. Prior to joining the IEA, Peter attended the University of Cambridge and the University of Bristol, obtaining degrees at both of those universities, both in engineering. Peter also worked in the private sector as an engineer for a number of years. Peter's going to give us an overview of the findings of the IEA study, and then we're going to have a little bit of a discussion around that and be joined by Jason Bordoff, who I think needs no introduction, but I'll introduce him anyway. Jason's going to offer a few reactions to the presentation and participate in some Q&A with us. Jason joined the Columbia faculty after serving as special assistant to President Obama and senior director for energy and climate change on the staff of the National Security Council, and prior to that, held senior positions on the White House's National Economic Council and the Council on Environmental Quality. In addition to teaching at Columbia's CEPA School, Jason is, of course, our founding director at the Center on Global Energy Policy. So without further ado, I'd like to invite Peter up to walk us through some of the study's findings, and then we'll have plenty of time for discussion afterwards. Peter, thank you.
Thank you very much, Katherine, and thank you all for inviting me here to speak, and it's a real privilege to come disseminate this report after working on it with my colleagues back at the IEA. So, as Katherine said, I'm here to talk about the Future of Petrochemicals publication that was released online on the 5th of October, and it's available freely on the website. You'll have to register to download it, but it's freely available. There are also Arabic and Mandarin translations available on the website, and there's copies of the executive summary printed out at the back if you'd like to take one with you. I'm sure I don't need to do this for this audience, but just to give a brief background of the IEA itself, just on a couple of slides. The IEA is an autonomous organization that works around the world to support accelerated energy transitions. It does this with data and access from its member countries and beyond. And this shows some of the IEA's family in a few slides. So the wider global family, its member countries, the 30 member countries, the association and accession countries, and partner countries. And then also the wider network of countries that the IEA works with to build its energy datasets. And so the IEA is using this data and its expertise in this area to look into what our executive director, not me sadly, but our executive director coined this phrase of blind spots in the energy system. And this started by looking at the role of the future of trucks, then the future of cooling in this year, and then now the future of petrochemicals. This series started in 2017, so it's relatively new, but this is the third in the series. So I'd like to start by giving an overview of the role of petrochemicals today in society and in the energy system, and also the role with respect to its role with respect to the environment. The first kind of perhaps obvious point to many of you, but one that's worth emphasizing, is that petrochemicals are all around us. In this room, we've got tables full of plastic bottles, plastic chairs. You'd never have to look very far in the built environment to see a petrochemical product. So just to draw out a few examples on this slide, on this infographic we produced. So there's a cluster of things that you find around the home and office, many personal items, digital devices, clothing, polyester clothing, and then in the background, PVC is an important material in buildings, plastic pipes, membranes, waterproof membranes in houses and damp-proof courses. Then we've got a set of products that are integral to our food supply and and even drinks and securing our food supply from the farm to the plate. So we've got fertilizers, pesticides, and of course packaging, both in the background, getting it from between businesses, but then also the consumer packaging that we all interact with. Then we've got another cluster of products that facilitate transportation. So we've got tires, plastics in cars, various fluids in a multitude of vehicles, acids and hydraulic fluids, all containing petrochemical products. And then finally, just to draw your attention to a kind of close to home topic for the IEA, petrochemicals are used in many aspects of technologies and products that we will need for the clean energy transition. Wind turbine blades here is an important example, lightweight carbon fiber composites and other materials, both of the future and traditional materials that we use today for these technologies. So now, taking a bit of a look back, petrochemicals have been, demand for petrochemical products have been growing very fast. And if we focus on plastics here in the context of broader bulk material demand, until the millennium, several of these bulk materials grew broadly in line with GDP, include aluminium, cement, and steel. After the millennium, many of these materials picked up their pace, broadly because of China's economic growth and development to support its huge explosion of infrastructure and construction projects. And then plastics, key group of petrochemical products, which I'll talk about a lot in this presentation, have grown faster than any of these bulk materials over this time period, growing by almost tenfold since 1970 and nearly doubling since the millennium. more than doubling since the millennium. This is explained in part by the fact that since the middle of the last century, plastics have become substitutes for many of the other materials in this picture and other materials outside it. This is because plastics are relatively cheap, they're versatile, and they can offer quite tailored solutions to a given material application. And sticking with plastics again, this group of materials will continue to be a big demand driver for the petrochemical sector. Advanced economies such as the US and Korea and Canada currently consume up to 20 times as much plastic resin as those of developing countries, such as India and many countries in Africa. Plastic demand is driven in part by domestic manufacturing industries to make other plastic products, but also by export markets. In 2016, the US and Saudi Arabia were the biggest export of polyethylene, which is a key plastic resin. Again, something that will come up quite a lot in this presentation. The largest importer was China, followed by Germany. Petrochemical sector is a very large consumer of oil and gas. Today, the sector accounts for 14% or 13 million barrels per day, MBD, of global oil demand, and 8% or 300 billion cubic meters of gas demand. So half of the chemical sector's total energy inputs are consumed as feedstock. And when I say feedstock, I'm referring to the fuels, oil and gas. The same fuels that are used to fuel the chemical sector are also used as its feedstocks, but these become physically embedded in the products themselves. So the molecules of oil and gas that are taken out of the ground, then becoming physically embedded in the plastic products that we use every day. This diagram shows how oil and gas, but also coal, are used as raw materials to produce different primary chemicals, and how they're then converted further downstream into commodities and ultimately consumer goods. Oil's the predominant feedstock for high-value chemicals, which are the main precursors to plastics. And then coal and gas are the main feedstocks for ammonia and methanol. And these are the main chemicals that we look at in the analysis. HVCs, or high-value chemicals, ammonia and methanol account for around 2/3 of the total energy inputs to the chemical and petrochemical sector. So you can imagine why we'd narrow our analytical scope to the 80-20 benefits of that selection. So when looking at the petrochemical industry in a more regional fashion, we can see that there's no one-size-fits-all for either production or feedstock use. So Asia Pacific, particularly China, dominates global primary chemical production, with Europe, North America, and the Middle East accounting for most of the rest. Translating this into the feedstock picture, there's also significant diversity among the shares of resources used in each region to produce these primary chemicals. If we look at the 4 largest regions, and these are regions I'll return to because they're important from multiple points of view, but very interesting on this feedstock diversity picture. Along with the Middle East, the US has a feedstock advantage in its access to low-cost ethane, owing to abundant supplies of natural gas and the shale gas revolution. In contrast, Asia Pacific and Europe rely mainly on naphtha, and when the spread between prices of natural gas liquids and crude is large, this puts these regions at a disadvantage in terms of feedstock cost. China constitutes a key outlier on the feedstock front because it uses quite a lot of coal as feedstock. Around a quarter of the feedstock used in Asia Pacific to produce primary chemicals is coal, and I think nearly all of that is in China. So these differences in feedstock choices across regions are a reflection of the big contribution of feedstock costs to production costs. In this slide, we're displaying simplified levelized cost to petrochemicals, which is a metric that can be taken as a proxy for overall production cost. The Middle East and the US remain the regions where producing these commodities from ethane is more advantageous, whereas naphtha-based production is less economical, but dominant in other regions due to their lack of access to low-cost ethane. The feedstock choice doesn't only impact costs, but also the process yields, so you don't get the same diversity of products from using ethane, so you have to use other on-purpose technologies to produce some of the products that are in deficit. Whereas naphtha produces lower amounts of high-value chemicals per unit of naphtha used, but then you get a better balance between the products you produce, ethylene, propylene, and the aromatics. So now looking at the kind of the petrochemical refining dimension, again, something I'll return to on subsequent slides. With growing demand for petrochemical products, oil companies, especially the refining components of the oil industry, are increasingly expanding into the petrochemicals business through what we call like refining petrochemical integration. And there are various forms of this that we go into in more detail in the report, various degrees and various models for doing so. But the current interest in petrochemical integration reflects the preoccupation in the refining industry to seek more resilient forms of revenue in the face of stagnating or potentially stagnating demand for traditional products. So in recent years, margins from selling transport fuels such as gasoline and diesel have narrowed, and selling petrochemical feedstocks raw is in many cases not profitable, as the prices for naphtha and LPG are often below the price at which it costs, below the cost price of extracting them, and the petrochemical path can offer higher margins by converting them into a more high-value project. And this slide shows some margins for the European context for fuels and for the petrochemical routes. And of course, integration between refineries and petrochemical plants can offer other benefits that you would have in any in more generic industrial integration benefits, sharing utilities, integrating process flows, capturing waste heat. All of those benefits are also able to be captured through greater integration, potentially. And as I said, integration comes in many different forms and flavors. For example, in the US and the Middle East, there are readily available natural gas liquids. So this leads the upstream petrochemical to refining, upstream natural gas liquid production and then petrochemical production as the prevailing option for integration. Many oil companies who produce NGLs have also invested in petrochemical production facilities, notably around the Gulf Coast, but there is no operational overlap as such between these facilities. In other regions where there's where availability of NGLs is limited, and therefore they use naphtha as a feedstock, the case for operational integration is stronger. From our analysis of this topic, it seems that the role of oil companies in the petrochemical sphere is set to increase, but in a variety of different ways. I've shown the US context, but we also look at the Chinese context, which is quite different. And then the last thing that I wanted to revisit in the kind of petrochemicals today section of the presentation is the environmental toll that petrochemicals take on the environment. The chemical sector is the largest industrial energy consumer. That's something that some people find surprising. They're not familiar with the energy statistics. And it's ahead of iron and steel and cement. Accounts for approximately 10% of total final energy consumption and almost 30% of industrial final energy consumption. However, the sector is only the third largest source of CO2 emissions. And this is because of this feedstock concept that I introduced earlier, that more than half of the chemical sector's energy input becomes embedded in the products themselves and is not combusted, not leading to CO2 emissions within the boundary of the chemical sector. But there are two important takeaways from this picture that maybe are in the background. Although feedstock inputs don't contribute to emissions within the chemical sector, they contribute to process emissions, and they can contribute to emissions downstream of the chemical sector, depending on how chemical products are disposed of and used. And secondly, although the chemical sector is the third largest emitter, it's still a very large emitter, approximately 1.5 gigatons per year of CO2, and then a further 300 to 400 million tons of CO2 equivalent in non-CO2 GHGs, greenhouse gases. So now I'd like to move to talk about one of the two futures that we outline, potential futures that we outline for the chemical and petrochemical sector. And the first one we call the reference technology scenario, and I'll spend relatively less time on this. And the reference technology scenario projects forward current trends that we observe today, such as announced capacity additions and things in the physical domain, but also takes account of firm policy commitments that would have an impact on the petrochemical sector. So we expect demand for plastics, one of the key drivers of the sector, to remain relatively robust. This diagram shows key thermoplastics that we analyze in detail, that we characterize in detail with in the modeling. As developing countries increase their population and wealth, these materials are increasingly in demand, and particularly sectors such as packaging and construction are key growth areas for these materials. On a per capita basis, demand for these plastics increases by more than 50% between 2010 and 2050, and on an absolute basis, I believe it's more than doubling. So now, in our base case, in our reference technology scenario, petrochemicals are the largest single driver of oil demand. They're expected to account for more than a third of total oil demand to 2030 and nearly half to 2050. Total oil demand rises by nearly 10 million barrels per day to 2030 in the reference technology scenario. This is across the whole energy system. And this is fueled by 5 key drivers. Shipping is an important driver here, and its importance looks diminished because it's in a category with other sectors that are declining. But around one MBD of shipping oil demand growth in the RTS by 2030, and this is fueled by expanding global seaborne trade. Passenger vehicles is the second one. Oil use in cars peaks in the mid-2020s, even though the global car fleet rises by 50% in 2030, and this leads to a 1.6 MBD increase. Aviation is number 3, and consumption in the aviation sector increases by about 2 MBD between today and 2030 because of the robust increases in travel demand, particularly in Asia. I believe it's oh no, this is to do with road freight, the India figure I have here, but road freight is number 4. Despite improvements in vehicle and logistical efficiencies, oil demand for trucks grows by 2.5 MBD, and this is driven in part by India expanding by a factor of 3 its transport demand for goods and services via trucking. And then the largest driver, petrochemicals. Oil for petrochemical feedstocks grow by more than 3 million barrels per day by 2030 in the reference technology scenario. While there are increasing efforts in certain regions to reduce the demand for single-use plastics and increase recycling, the overall underlying demand for these materials outweighs these efforts. And in terms of where this demand and production takes place, or where the production side takes place, this slide shows the regional distribution. China and the US show the largest near-term capacity additions as a result of the feedstock advantages that I was talking about earlier, and in China's case especially, a strong source of local demand for manufacturing. Longer-term growth is led by the Middle East, and then the rest of Asia still, and particularly China. By 2050, Asia-Pacific retains its position as the largest chemical producing region. And I should draw your attention to this graph. It's quite small there, that the axis for Asia-Pacific is, I think, 3 times the scale of the other graphs. So when looking at the 4 key regions that I mentioned earlier, Europe, Middle East, North America, and Asia-Pacific, we if we can zoom in on the exact feedstocks they're using in each year here. Ethane feedstock consumption for high-value chemicals grows by 70% by 2030 in the favored regions, so the US and the Middle East, North America and the Middle East, but mainly the US. And in part, this growth is as a result of exports of petrochemical products to Europe. However, regions with continuing strong growth in the long term rely mostly on naphtha. So this ethane kind of expansion in the shorter term in the Middle East and the US is not a sustained thing throughout the scenario. Longer term growth shifts more to naphtha as the availability of ethane and NGL supply tightens in the late 2020s. And then just a quick look here at ammonia, which is a key precursor to most nitrogenous fertilizers, all nitrogenous fertilizers, I believe. Mainly natural gas across most regions, across the important regions we identify, but then this strong but flattening use of coal in Asia Pacific, and again mainly in China. So I'd like to move now to just talk about the alternative future that we envisage for the petrochemical sector, or that we project forward. And actually, it's not projecting forward. This scenario is very different to the reference technology scenario. We start with a goal. I'm sure some of you are familiar with the IEA's other scenarios. The Sustainable Development Scenario provides the global energy system context for this deep dive into the chemical sector. And this starts from a series of goals that we want to get to, sustainability goals, and then works backwards to what we need to do to get there. And so more specifically, where we want to get to is a more sustainable chemical industry that can provide the world with its products, but address several of the environmental challenges that it faces over the coming years, including aspects of the United Nations Sustainable Development Goals, or SDGs. Just calling out a couple of those specifically, SDG 7 to do with renewable energy, and SDG 13 to do with climate action are obvious ones for the IEA to look at, given our remit in clean energy and the energy sector accounting for the majority of anthropogenic CO2 emissions. But we also cast the net a bit wider in the spirit of the sustainable development scenario, and look at broader aspects of the SDGs. In this analysis specifically, that translates into the consideration of air pollutants, water pollutants in the form of plastic pollution, and water demand alongside CO2. And here we have the RTS results, the reference or baseline results, and then the CTS results. And the environmental impacts of this scenario decline rapidly. By 2050, air pollution declines by 85%, water pollutants and the form of plastic pollution by more than 90%, and CO2 emissions are around 45% lower in 2050 than they are in today. And the next few slides take a deeper look at how that's achieved. So the first element of context to look at in the CTS is the CTS of the clean technology scenario, if I wasn't clear about that, CTS and RTS. So the first element of context to look at is the demand for primary chemicals and the role of recycling in reducing the demand for primary chemicals. So demand for plastics can be satisfied either by primary production from oil and gas, or it can be satisfied by recycling existing plastic products and therefore not adding to additional primary chemical demand. The purple bars on this slide show the dramatic increases in secondary production that take place in the CTS relative to the blue bars in the RTS. The red dots overlaying the bars show both the average and the range of recycling rates, this is collection rates, across the resins that we analyse. And the resins that we analyse were shown in that first very colourful graph in the RTS section. I can go back to that later if you'd like to look at it more. And then finally, the green bars show the resulting primary chemical savings from these increases in collection rates. And the results of the CTS are more than 70 million tonnes of primary chemical savings by 2050, or around half of today's plastic production taking place via secondary routes. So plastic recycling also has a big impact on oil demand for petrochemical feedstock. Higher recycling rates in the CTS reduces oil demand for feedstock by 2.4 MBD by 2050. However, oil demand for chemical feedstock in the CTS, in the context of declining demand or stagnating demand in other sectors, still grows by 3.6 MBD, reaching more than 15 MBD in 2050. The share of chemical feedstock in total oil demand in the CCS is actually much higher than in the RTS, and that might be intuitive to lots of you, but it's an interesting finding for us. And by 2050, petrochemicals account for more than a quarter of the global total for oil demand in this clean technology scenario, much higher than the roughly 16% in the reference technology scenario. And just to reinforce this point about the new oil demand dynamics in the clean technology scenario, this is an interesting finding that we were able to pull out. Here we have some regional per capita figures for oil demand for road passenger transport, and then also for plastic consumption, the oil required to satisfy plastic consumption. Today in the US and the EU, per capita oil demand for road passenger transport is between 2 and 5 times as much as for plastic consumption. In China and India, the ratio is smaller, but road passenger transport still eclipses that for the oil demand for road passenger transport still eclipses that for plastic consumption. So this interesting feature of the CTS is that in all 4 of these regions, per capita oil demand for plastic consumption overtakes that for road passenger transport by 2050. And petrochemicals, as I've said before, have become the largest sector of oil demand, reaching more than 15 MBD, far higher than the 7 MBD for road passenger transport. So despite this continuing growth in oil consumption in the CTS, emissions declined by about 45%, showed on the environmental slide, the introduction to the environmental slide. 45% relative to today's levels. This represents a 60% decline relative to the RTS in 2050, where it would have gone, or a 25% cumulative reduction in CO2 emissions during the analysis period. So how can oil demand keep rising and emissions go down? Well, one of the reasons goes back to the feedstock element, that a lot of this oil is actually being embedded in physically in chemical products. But then there are also other things taking place in the CTS that drive emissions down. Sorry, that's the cumulative emissions there in the yellow dots. Cumulative emissions savings, rather. So I've grouped the emissions savings by lever here in this pie chart. This is all available in more detail in the report. But there are 5 main categories: carbon capture and utilization and storage, CCUS; coal to natural gas feedstock shifts, which is particularly relevant in China; energy efficiency; plastic recycling; and the use of alternative feedstocks. And you can show you can see the shares there in cumulative emission savings terms. CCUS does the heavy lifting on the emission savings front. The chemical sector represents some of the lowest cost applications for CCUS in the energy system. And it is hard for, according to our modelling, it's hard for alternative feedstocks to compete with these relatively low cost opportunities for CCUS. When I talk about alternative feedstocks, so we're going to have one more slide on this after this, but we're talking predominantly about bioenergy and electrolytic hydrogen. Energy efficiency, both from a continuous improvement point of view, so the specific energy consumption of process units improving gradually over time, but also from fundamental process shifts to just process routes that are more energy efficient inherently. These shifts deliver around a quarter of the savings. And then coal to natural gas shifts, so reducing the process emissions resulting from producing primary chemicals yields about another quarter. Ambitious increases in recycling that I showed on the previous slides deliver around 9% of the cumulative emission savings, and this is as a result of having to produce fewer primary chemicals. And so just to provide a bit more detail here on the key emissions lever in the CTS, which is CCUS, The chemical sector hosts the largest CCU application that's around today, which is the use of concentrated CO2 streams from ammonia production as feedstock for urea production. So when people talk about CCU and all of the future applications, this is by far the largest one that happens today. However, this is a temporary storage mechanism. CO2 from urea that becomes embedded from ammonia production is then released downstream when urea is applied to fields. The urea decomposes and the CO2 molecule is released. So this is only a temporary application, but it's important to consider it in the chemical sector modelling because you don't want to overestimate the cheap sources of CO2 capture for storage. By 2050, though, capture for permanent storage overtakes the current application of utilisation, with around 220 million tonnes per year being stored and being captured and stored permanently. And so this means by 2050, again, that 35% of emissions generated in the sector are being captured or utilised by 2050. It's a lot of dots there, but shows the rate of utilisation and storage in each year in each scenario. Now I wanted to touch on one of the key environmental problems that's garnering a lot of attention around the world to do with the energy system more broadly, but it relates quite clearly to the chemical and petrochemical sector or its products, and that's plastic leakage into the world's oceans. When disposed of improperly, plastics can and they do make their way into waterways and eventually into the ocean indirectly or directly. And when they do, they can get broken down by sunlight into tiny particles, which then many fish and other animals can ingest and mistake for food. In the RTS, the base scenario, with no current firm commitments and coordinated across multiple jurisdictions, which is one of the things we think it will take, with none of those commitments established, cumulative plastic waste leakage into the world's ocean increases more than tenfold over the scenario horizon. In the CTS, rapid and broad-based improvements in waste management to facilitate this near tripling in collection rates that occurs in the CTS lays the groundwork to dramatically reduce the cumulative waste that's flowing into the world's oceans. And I should mention that this doesn't take into account any efforts to remove plastic waste from the oceans. This is additions to plastic waste leakage. So our analysis of investments associated with primary chemical production shows that the CTS, our clean technology scenario, can be pursued cost effectively. Recycling and coal to gas feedstock shifts in the CTS mean that cumulative capital investment required is actually lower in the clean technology scenario than in the reference technology scenario, which is often a surprising finding. This is because recycling means that you have to lowers demand for primary chemicals and means you have to build fewer expensive pieces of equipment like steam crackers that cost a lot of money. And also the second component, this coal to gas feedstock shifting, the capital intensity of coal-based chemical production is generally higher than those utilizing gaseous and liquid feedstocks. So shifting away brings an environmental benefit and also reduces the capex required. And these savings from these two key elements of savings offset the costs that are required for additional storage, carbon capture and storage equipment, or carbon capture equipment is the investment that takes place in the chemical sector. So this last graphic displays some results from an off-model analysis that we performed to examine these alternative feedstock routes in greater detail because they didn't come through as much in our modelling. They didn't prove as cost-effective as CCUS in our modelling, so we wanted to take a bit of a more detailed look. And I should stress that these results don't form part of the CTS, but they are kind of a side analysis that we did. So feedstocks were produced from a carbon neutral energy source. The benefits would be the elimination of downstream additional emissions, and if products are oxidized during use or disposal, these emissions would either be neutral or they would not occur. And also theoretically, the chemical sector could then move away from using fossil fuel feedstocks and fossil fuels altogether. So firstly, we looked at a bioenergy only pathway. This entails producing ammonia and methanol directly from bioenergy via gasification, and ethylene from bioethanol via dehydration. And then the propylene and the aromatics, for which there are not direct commercial routes available at the moment, or direct proven scaled routes. Methanol to olefins and methanol to aromatics are used to convert methanol into propylene and aromatics. And then secondly, we looked at an electricity-only pathway. So this is using electrolysis, water electrolysis, to produce methanol and ammonia directly. And then again, using the methanol to olefins and methanol to aromatics processes to convert methanol into the olefins and aromatics that are required in the CTS. The CTS demand projections were used for this side analysis. That's why the CTS crops up. So the results are pretty stark. By 2050, the bioenergy pathway requires nearly 8 times the bioenergy demand for all industry in a similar low-carbon pathway, in an SDS-type world. And in the electricity pathway, the demand for electricity exceeds that for all industry by 25%, again in a similar SDS-type pathway for industry in 2050. This is significant because industry is a very large electricity consumer. There are other challenges that are explored more in the book in these to do with these electricity and bioenergy only pathways, to do with water demand and the large amount of CO2 required for the electricity pathway in a world that you would imagine would be fairly heavily decarbonized by that point. And just to draw your attention to the dashed bars, which are very faint on the screen, but the dash bars show the additional energy requirements where all of the chemicals that are currently being produced in refineries were also produced via these routes. It might be a bit odd to have oil refineries still going, but your entire chemical industry not utilizing fossil fuels. So we wanted to get some idea of what the total shift would require. So now returning back to the CTS and the policy recommendations that we think would be required to get us there, or some of them, we divided these top 10 recommendations into 2 groups. The first set is more associated with the production of primary chemicals, whereas the second set is to do with the use and disposal of chemical products. So we have some. I don't want to use too much time. We can discuss these in more detail, and they're written down here. But I think these first 5 recommendations will be quite familiar to those who read in-depth IEA reports about specific industrial sectors. We need to stimulate R&D to develop and scale up the sustainable chemical processes. We need to establish benchmarking schemes for energy efficiency or extend them where they exist already. We need to pursue effective regulatory mechanisms for reducing CO2 emissions, whether it be taxation, pricing, etc. And these are broader things that apply to other elements of the energy system as well. We need to require industry to meet stringent air quality standards like those of the World Health Organization, and also ensure that fuel and feedstock prices reflect their actual market value and some of the externalities that are associated with using them as opposed to other feedstocks. And then more to do with the use and disposal of chemical products. These are perhaps less familiar. Sorry, I've skipped one slide there. So we've got things like reducing reliance on single-use plastics other than for non-essential, non-substitutable purposes. Very important, one, number 7, about improving waste management infrastructure, both to enable the dramatic increases in recycling that take place in the CTS, but also the added benefits of reducing plastic leakage. Raising consumer awareness about recycling and other important demand-side measures. Designing products, incentivizing designers to design products with disposal in mind, so making them easier to recycle, easier to collect. And then initiatives to extend producer responsibility, incentives to extend business models and other schemes that extend the producer's responsibility beyond the factory gate. And that's it. My conclusions are there, but I don't think I'm going to read these out. These are more or less the high-level themes of the talk, so we can leave those up there for the discussion. Thank you very much.
Thanks so much, Peter. That was really interesting. Again, for those watching online and listening to the podcast, my name is Katherine Spector, and I'm here with Peter Levi, Energy Analyst at IEA and co-lead author of this report that we've been discussing, the IEA's report on the future of petrochemicals. We're also going to be, come on up, Jason. We're going to be joined by Jason Bordoff, who is, of course, our founding director of the Center on Global Energy Policy. I would just like to remind any of you who may have questions, if you're in the audience, we're going to do a little discussion here first, but at Q&A time, please feel free to come on up to the microphone. And for those of you watching online, again, you can use the hashtag CGEP events to ask a question, or our Twitter handle at Columbia U Energy to ask a question if you are not in the room. Join you at the table, I think. But Jason, just to begin, can I ask you to just share your thoughts on this report and the future of petrochemicals?
Yeah, well, sure. This is great. I appreciate Peter's being here and the work the IEA did on this. I think it's a really important question. I don't have unique insights into the answer about the future of petrochemicals, but I think it's really an important piece of work because I don't think that the role of petrochemicals play in the CO2 mix is often well understood, and in the outlook for oil demand is often well understood. And those two things don't necessarily line up one-to-one in petrochemicals the way they do when we think about oil use when it's combusted in the transportation sector. So I think that's something that we're at the Energy Center focused on. Antoine Haff just walked in, who is our resident oil market expert at the center and is doing a lot of work with Katherine and with Marianne Kahn and some others on the future of oil demand. And that is a pretty hugely important question for the climate, for oil markets, and gets, I think, sometimes superficial treatment because people get quite understandably and rightfully excited about some of the progress we've seen with electric vehicles, still quite a small share of the total, so even small very large growth rates take a long time to make a dent, but then, of course, passenger vehicles are still only 20 or 25% of global oil demand. So thinking about how it looks in freight or in maritime or in aviation or in petrochemicals is really important, and that looks very different in different parts of the world. So I think this is a really valuable contribution. I just want to make sure and so the takeaway from that, I presume, Peter, is if people were to see numbers that show like hypothetically, if we were to see very rapid growth of electric vehicles or something, and you said, well, we're going to see a 5 million barrel a day decline in oil demand as a result of the expansion of electric vehicle, and a 5 million barrel a day growth because we're seeing rapid growth in the use of petrochemicals, the immediate reaction might be, well, we haven't made any progress at all. And in fact, we would have from a CO2 standpoint. I just want to make sure that's correct.
Am I doing this right?
Nope,
yeah.
just on.
Okay, cool. I mean, that is correct. I think it's important though that we don't say that embedding oil in petrochemicals is 100% good. Mm-hmm. We have emissions that take place in the chemical sector that do stem from feedstock, so process emissions, although these are relatively small compared to the complete combustion of the fuels in the transport sector. And then we also have these other pollution problems that I'm sure we'll get to.
No, those are really important. I want to make sure we understand like what problem we're addressing and what problem we're looking at. And when you showed process emissions and you showed energy-related emissions. So if we were to see progress in decarbonizing the energy system, that presumably would change how we think about the CO2 impact of growth in petrochemicals and what that would mean for the future of oil demand.
Yes. So, the energy-related and process emissions that are shown on the chart are those that take place directly within the petrochemical sector. So those are not from electricity. Those are direct emissions within the chemical sector. And a lot of those are from high temperature heat, which is another challenging aspect of decarbonisation that we're facing in lots of industries, but the chemical sector's no exception there. And then the process emissions, if you're using a fossil fuel feedstock and you're producing something with a lower carbon balance than what you put into it, it's relatively difficult to get rid of those with the laws of stoichiometry. But you've got obviously important measures that you can take with CCUS and the other things we discussed.
Which is why you look at CCUS, right,
yes,
as part
absolutely.
of the solution. And then you showed a chart, just trying to find it, but you had one that showed like the different pathways in the sustainable scenario and what the sustainable development scenario or clean technology scenario.
Sorry, we call these specific deep dive ones slightly different.
The very steep decline in water pollution relative to what it would otherwise look like, decline in air pollution, and then in CO2. I was just wondering, in that scenario, what does oil demand look like in that clean technology scenario? Does that make sense?
Yeah, so...
Because it's not going to decline as steeply, I think.
Oil demand...
You show the growth in oil demand in the petchem sector.
Yeah, no, absolutely.
And in the clean technology scenario, what happens to the growth of oil demand? How much does achieving that clean technology scenario affect oil demand in the petrochemical sector? Or are we achieving through CCUS and other things, and you obviously have embedded carbon as part of oil demand, do we still see... Actually, it doesn't hit oil demand that much to achieve the clean technology scenario. Does that make sense?
Yeah, no, absolutely.
Okay.
Sorry. So the key difference in oil demand for the petrochemical sector between the two scenarios, between the reference technology scenario and the clean technology scenario, is the impact of recycling on reducing demand for primary chemicals. We assume the same demand for plastic materials, but the way they're produced requires fewer primary chemicals and therefore less oil use as feedstock.
You'd still see growth in oil demand for petrochemicals in the clean technology scenario?
We do. I think the exact figure, I don't want to re-quote it wrong, but it's shown on one of the charts earlier in the presentation.
Okay, maybe I missed it. Sorry.
No, it's fine.
I remember the growth in the reference case. I think it was 3.6.
Yeah, absolutely. There is still growth, and then its share in the overall global oil demand is shown on the right-hand axis. But so there we're looking at around 15 million barrels per day in 2050 from around 13 today.
Right. So
and sorry, this just to clarify that this is feedstock. So we're looking at 11.7 today. Most of the oil that's consumed in the sector is as feedstock. But then there's a small amount for process energy.
And then I should have worn this jacket that I forgot to wear that is made of recycled plastic from Adidas. And I was wondering how much things like that matter. So everyone's upset about we're going to ban plastic straws and I shouldn't have a plastic bag when I go to the grocery store. So we see the very visible things that we can do. But as you said, these chairs are made of... So we're worried about plastic ocean pollution, and we're taking steps that are visible to the consumer, like straws and plastic bags. Let's imagine we do all those things. Does that really matter?
Well, it certainly matters, but it's definitely it doesn't produce as big an impact as one might think. So in the clean technology scenario, we characterize the recycling rate as a combination of three factors which multiply, and that's an important dynamic of recycling that's not well understood, I don't think. So the first thing is how much of the available plastic waste that there is, how much of it do you collect? And that's the main thing that's quoted when we talk about recycling rates. So when we see very high recycling rates quoted in Germany, Japan, Korea, usually that's referring to the collection rate. So that's factor number one, and that could theoretically be 100% of what's there. So you'd have to do a lot of sifting, a lot of very careful sorting at the consumer end, but you could potentially get all of it. You then have the yield loss that takes place when you recycle. And at the moment, this is typically 20 to 30% of the plastic that you collect that is dirty, needs to be washed, then needs to be melted, reprocessed. You lose 20 to 30% of it. That can be improved, but it won't be no loss in the future, we estimate. And then the most important factor that is, I don't think, well understood at all is this the extent to which recycled products can displace primary products. So if you recycle your PET bottle as polyethylene terephthalate, I hope, if you recycle it as is quite commonplace into polyethylene terephthalate fiber, that's a one-time deal. So you do that once to make your, what I'm sure is a beautiful jacket, and then it's a jacket forever. And fiber recycling at the moment is very small scale where it exists at all. It's a relatively limited avenue for recycling, at least with current technology. So this kind of downcycling effect that we get from a lot of recycling is an important factor in that. When you have very high recycling rates, this doesn't necessarily mean huge one-for-one displacing of oil demand used to produce that original product. I'm sorry if that is, I'm not sure if I explained that very well, but those three factors are important, and the fact that they multiply together is something.
I guess the other way to say it is, like, if there is people talk about like a backlash against plastic pollution, and that tends to take the form of very tangible things like straws and plastic bags. I'm oversimplifying.
Yes.
But if that becomes much more widespread, I see it with students, I see it with my daughter, I see it right, that is gaining traction. If that becomes a norm, if we see a cultural norm where people will like look at you like something's wrong with you if you take a straw in a restaurant or a plastic bag in a store, does that have much impact on your outlook for petrochemical demand for the oil sector?
So, I mean, single-use plastics is something that's used, is a term that's used to refer to those types of applications quite a lot, and there's no clear definition of that. So, whilst we can definitely envisage a world in which we don't use too many straws, there are lots of other plastics that are used once that are designed specifically because they can be used once. So you've got medical supplies and equipment. There's stuff like that, nappies, and lots of things that contain.
Nappies are diapers, by the way.
Sorry, yeah. And I'm sure not all of them contain petrochemical products, but lots of products that we would find much harder to envisage or whimsically kind of get away from or change our behavior with. Lots of single-use products are much harder. And also there's very limited, firstly, data, but also even clear definition of what single-use plastics are. And you'll see a few estimates out there. We found a couple of other, I think some large oil companies have made estimates of what single-use plastic demand will have as an impact on oil demand, but we couldn't clarify the definition robustly enough for us to feel comfortable putting any numbers to that.
I think I've accidentally slipped into the moderator role since just force of habit. But I'll turn it. I'll be quiet now and give it back to you.
I'd just like to sort of piggyback on that question about the scope for reducing initial use as opposed to recycling. And one of the charts that I really liked in the big report that was not in your presentation was one that looked at how both fertilizer demand and plastics demand grows with GDP per capita. And it's not unlike charts I've seen for other types of oil, where it grows extremely rapidly as GDP per capita starts to grow and continues to grow, but sort of plateaus at the very high income levels and looks almost sort of logarithmic in that way. So that sort of answers the income side of the question. But when we think about initial use, again, as opposed to recycling, I'm curious if you, the IEA, have given any thought to the price sensitivity of demand, whether in the emerging world or the developed world. And I guess the sort of point of that question would then to be that if governments do decide that reducing consumption, particularly of single-use plastic, is a policy goal, would price be an effective lever or not really?
The short answer in building our demand projections for this work is not directly. We haven't taken into account specific end-use prices for plastic products. One of the barriers to doing that at the moment is, and you mentioned it in your introduction, is that to get to primary plastic and fertilizer products, to get even to data on consumption of those products, this is before they're converted into consumer products and other things and used as building materials. That aside, which is another step, it's very, very difficult to get decent data on the end-use consumption of those things, never mind the prices at which they're consumed. I mean, I'm sure that we can make certain estimates, but in terms of making a robust estimate of elasticities and things like that, I'm afraid we're not at that stage with this topic yet, and I feel that that's a fairly broadly faced challenge with this sector. The one of the really kind of exacerbating factors on the data front is the multiple slices of trade that take place. So you've got trade that we do try and take into account the potential for trade in the future at the primary chemical end, and we talked quite a lot about the various advantages that each region will face and the potential advantages that will provide for them as an export region, for instance, US, Middle East in the short term, and then the domestic drivers for that demand. But then beyond the primary chemicals that we model, all of the second tier, third tier chemicals that are within the chemical sector, and then the products that are made outside it, the trade that happens at all of these levels is phenomenal, and it's much more it gets exponentially more complex as you go towards the consumer. So that's my excuse. But, yeah.
Yeah, it's tremendously challenging data-wise. I wonder if, given the sort of mainstream attention to some of these issues, we might start to get some case studies. I think municipalities probably know what their waste collection and disposal costs are. If that were somehow added as a tax or a fee, at least in sort of little microcosms, we might start to be able to measure a demand response. But it is a really overwhelming data problem at even a national level in the U.S., let alone a global level. So that's really why this report as a starting point was tremendously helpful. I want to switch over to the feedstocks for just a minute, because the other problem with this sector that I find a little bit overwhelming to wrap my head around is what the implications are for refiners. We have a world where refiners are now looking down the barrel of reduced or at least slower growing gasoline demand. In many cases, a slower growing or reduced heavy end residual fuel oil part of the barrel, and eventually, as you said, a higher naphtha demand. But in the meanwhile, the competitiveness of ethane might be a bit of a hurdle. So what is a refiner to do when you start to get these very sort of lopsided rates of growth in the different products? How are they particularly going to get over that hump and adjust? Yeah. We see a lot of companies and even countries sort of saying, this is where it's at for us in terms of our future economics, this is where we're going. But if you could just maybe talk a little bit more about the challenges that refiners will face in the next sort of 20 to 30 years in making this transition.
No, absolutely. So this is a topic we revisit at various points in the book. And in the reference case, or the baseline scenario, we already see some of this tension in terms of the ratio of different weight products within the barrel getting out of sync with what it's traditionally been. But then in the clean technology scenario, this slide actually demonstrates it quite well. Most of that blue bar, most of that feedstock there is we have ethane and LPG and oil products in the IEA in our balances, and these are even lighter than naphtha, and then most of the rest is naphtha. Very small amount of gas oil uses feedstock, diesel, and very small amounts of heavier products. So the imbalance becomes even more acute in a clean technology scenario, given that gasoline and diesel are undergoing even more severe declines and stagnation. So absolutely a key concept that we return to, and I think the CTS dynamics are the most interesting ones to look at. In terms of what the refining industry might do about this, or one thing is the integration aspect that I touched on a bit in the talk. That on the financial side, as the margins are reducing in the traditional markets, trying to get step further down the value chain in the petchem sector to try and capture some of that margin that's being captured by chemical companies or only chemical only companies. So that's one thing that we already observe happening. And then in the longer term, the dream technology, and in fact there is an existing plant today of so-called crude oil to chemicals.
Yeah. I was going to ask you about that. I mean, Aramco's looking at it, right? And,
and there's an I think it's run by Exxon. There's a plant in Singapore today that's big-ish, 400 kilobarrels per day, and there's the extent to which this is other technologies pieced together, so bits of petchem facilities and bits of refineries stitched together. I must confess that on the refining technology level, we would be of great benefit to have Araceli, the other lead author of the project here. She's very experienced in the refining industry. But the extent to which these technologies are pieces of each industry stitched together, and not a full revolution in the way that oil is processed and leapfrogging this refining step. That's something that is set to evolve in this, or will need to evolve further if it's to fulfill the full ambition of the technology, which is getting 70 to 80% yield of your crude into chemicals. And this, I think, you need very light crudes to do this at the moment, or even very condensate. Yeah. So you're utilizing things that are already much closer to the feedstocks that we might be short of later. One other component to mention on this front is that the lighter crude supply that's coming from the US oil and NGLs from the shale gas revolution are to some extent looking like they will fill some of this additional light product gap in the short to medium term. But as we see the NGL supply tightening in the latter half of the next decade, based on current projections of output from the US, that's when the challenge will start to really ramp up, according to our modeling.
Sure. Before we open things up to the audience, Jason, do you have any?
No.
Okay. Again, if you're in the room here, please feel free to step to the microphone. And for folks listening, again, if you'd like to ask a question virtually, the hashtag to do that is CGEP events, and our Twitter handle is @ColumbiaUEnergy. Would anyone like to begin? Oh, I'm sorry.
Thank you very much for an excellent presentation on your report. I'd like to ask two big picture questions. One is, I'm thinking about this from the point of view of alternatives to oil and gas, and thinking of the consuming sectors. And obviously power generation is under attack, if you will, with alternatives to what we have now, whether it's renewables or nuclear or other ideas which are going to lower. Obviously, they have already lowered or displaced oil, but they might even lower how much natural gas is used. The same thing with transportation, obviously, with electric vehicles, et cetera. But it seems to me that petrochemicals doesn't have this alternatives, clear-cut economics. I wonder if you agree with that long term. I'm talking about 2030 to 2050. And imposing on that, I'd like your opinion about, especially in Europe, which seems to be going ahead with a carbon price. If you assume a modest carbon price, let's say $20 per ton of CO2, or what I consider a more realistic carbon price, which is $50 per CO2, which is not unheard of in Scandinavia, which has over almost $100 per ton today. How do the economics look for the petrochemicals technologies, the CTS, as well as the RTS and the biofuels? And thirdly, do you see that you made a projection about less availability of ethane because of natural gas, but have you taken into account long-term the possibility that shale technology, horizontal drilling, and fracking is going to move outside the United States in other areas that have shale, that are looking at it, including China and others, and therefore more natural gas might become available, and therefore it's going to be in competition for both power gen as well as potentially for petrochemicals? I wonder that those kind of long-term views, I'd appreciate your opinion and definitely Jason's opinion.
Well, perhaps. So a few reflections. I have to remember these points. So on the alternatives point first. So yes, there are alternatives to using oil as a feedstock for petrochemicals and natural gas and coal. Theoretically, any carbon hydrogen containing compound is a candidate, but obvious ones are bioenergy and then electrolytic hydrogen. So water electrolysis to produce hydrogen and then combining it with a carbon source, usually CO2, to use it to make methanol and ammonia. And those are two routes that we characterize in detail for the primary chemicals in the chemical sector. The difficulty and the reason, and I think this is moving more to the second question, in the context of the broader energy system and the chemical sector playing its role within that, the reason why these technologies don't see as much penetration, given a level of carbon price or a broader context in which they might be more appealing to the modelling choices, more appealing among the modelling choices. The reason for that is that CCUS is able to reduce the emissions, keep the oil feedstock that is comparatively cheaper in a lower carbon world where other sectors are moving away from it. It's able to utilize this feedstock, capture it at relatively low cost, and then send it for transportation and storage. So of the scalable long-term alternatives, that's the one that, according to our modeling at the moment, wins out. With a lower electricity price, potentially with very low electricity prices from surplus electricity or maybe from stranded renewable assets. So we're looking at that at the moment as well. If you had super low electricity prices, then these routes can become competitive. And we actually produce a graph towards the end of the report where we do this off CTS analysis, where we look at for electricity prices right down to the 10 to 20 euros a megawatt hour, which of these technologies are competing at what cost and for a given set of gas prices and feedstock prices for bioenergy. So that I hope I've answered a couple of the first ones with that. On the ethane and LPG and NGLs in general supply, I think Jason probably would like to talk about this for longer than me, but the NGL supply that we see in the US, it comes from the broader modelling that we do of different gas fields and oil fields around the world. We have colleagues on the supply side who look at all of those fields individually, I believe. They look at trade, they look at likely yields and that kind of thing. And the supply of NGLs, specifically the dampening effect or the lowering of relative supply despite continuing natural gas production from these assets and fields, is because as the shale gas operations move to fields further along the supply curve, they are drier. So there are fewer NGLs in the gas stream. That's my understanding of it. And that's where this flattening supply of ethane and LPG comes in the modelling. And I assume that effect is modelled within the other regions as well, that where shales looked at. But I might refer you to the supply colleagues on the World Energy Outlook side for a detailed discussion of that topic.
There were a lot of pieces to the question, so I may have lost the thread, but I'll just make a point. You asked about CO2 pricing and the impact that it would have, and so I think there's a question, which is what impact a given CO2 price would have on the competitiveness of it, and you may have thoughts about that in your modeling. One point I would make, I think, is important to keep in mind is the kind of political economy of carbon pricing and how we actually see carbon prices get implemented and designed, both to build political support and because almost any carbon price regime is likely to have border adjustments built into it to protect the competitiveness of the manufacturing sector. Petrochemicals would be one that would be seen as very vulnerable to being undermined by a carbon price if your competitors overseas were not paying a similar carbon price. So I think it's, in terms of your policy recommendations, I see the petrochemical sector as, tell me if you agree, being one of the more difficult ones to actually impose a carbon price on, because it's always going to get caught up in this trade and competitiveness argument that's likely to mean even countries that move forward, or states or whatever, with a carbon price may end up actually exempting large segments of the manufacturing sector that could include petrochemicals. We've seen that where carbon pricing has been implemented so far. I think you asked about shale outside the U.S. as well, and I think that we know the resource is there. Shale is not unique to the U.S. by any means. There are, of course, more challenges with infrastructure and water availability and private land ownership and other things. But given the right incentives, I think we're already seeing it developed in Vaca Muerta in Argentina, and it will get developed elsewhere. There's also some benefit to it because it's more short cycle in nature, and as there continue to be growing concerns about long-term oil demand growth, there's some desirability we see on the part of the industry, which is increasingly shifting capital toward things that are short cycle. Shale might become more attractive for that reason.
I would just add on the industry kind of carbon leakage point that for sure that's something that we hear from our industry stakeholders, but not just in the petrochemical industry, but we engage on 5 energy-intensive subsectors, specifically in the technology division: pulp and paper, cement, iron and steel, aluminium, and chemicals. And this is a relatively common theme that people with industries with relatively older assets in places like Europe, with the most likely integration of some of these policies, say that, well, if we have to rebuild these plants, it won't be here. And that kind of message coming through against that policy push. But it's obviously hard to predict what the adjustments and kind of policy compensations would be put in place for those kind of adjustments.
I think Mark may have had a question. Someone more knowledgeable than us.
Mark Schwartz, Platts Analytics. Very, very interesting talk and very important topic. We come to almost exactly the same conclusions about the importance of petrochemicals. I think you mentioned the term cost-effective recycling. So I'm wondering, in the study, did you take a look at the economics of recycling versus primary plastics production? Where do we see cost-effective recycling today? What's it going to take to get there? Is the market going to get there? Do they need a little help from carbon fees and other fees on one-time use? What can you say about the economics?
So the investment numbers, it's important to clarify, refer only to primary chemical production. So when we are talking about recycling, the secondary process equipment, that's not included within those figures, which does lead to a bit of a distorting effect in terms of the investment. But the very expensive assets upstream in producing primary chemicals are an important consideration. In terms of the economics of one versus the other, I think this very much depends on the type of recycling. On the plastics front, I assume you're referring to many. And so you've got 3 main types as we characterize it in the report, and more generally mechanical, chemical, and then back to feedstock. And as far as I am aware, the chemical and back to feedstock level recycling is at demonstration phase and relatively early on in the development stage of really not many processes brought to market, as far as we're aware. Mechanical recycling, well established, can be cost effective if there's the right incentives and if a lot of the collection and sorting processes are handled or taken care of by the municipality or by a third party. I think, for PET, for recycled polyethylene terephthalate, these chips have a market price, and when oil prices are high, some producers, I think, switch to larger chunks of secondary production. So in specific market segments, as far as I'm aware, there are aspects of already kind of cost competitive elements to recycled and secondary plastic production, but nothing like the scale that we need. It's as far as I'm aware, the most recycled plastic resin is PET, and it's because it has a high value application that can be recirculated, and it has this big downcycling opportunity to fiber. which is a huge market that then has no recycling associated with it. So I think in specific segments, in specific elements of the cycle, you can see some cost competitiveness. But I think in the full gamut of recycling options, you see relatively limited cost effectiveness. That's my insight.
Thanks, Mark. Terry?
Just a question on the top-down analysis.
Could folks just introduce yourselves?
Oh, yeah, sure. I forgot that part because you said, and I just jumped. Yeah. So Terry Vishwanath, I'm with S&P Analytics. So just a quick question on the top-down analysis. I think that chart was really great. You talked about the difference between industrialized versus emerging nations, the 20 to 1, and then the 10 to 1 in fertilizers. We've seen some changes occur within these components. So, for example, over the last 4 years, China has actually decreased their percent of fertilizer application per crop 15% each year, 2014 to 2018. You're seeing a shift occur within these segments. Can we assume all size fits one when we think about doing that analysis? Because we all kind of juggle with it. But what do you think?
No, absolutely. I think there's, especially on the fertilizer front, for nitrogenous fertilizers, there's significant gains still to be made on the efficiency, in the application efficiency front. There's been lots of academic papers written about this in the past, but I think this is really gaining traction in the policy sphere and in the technology sphere. So perhaps these multipliers won't come to their full fruition of multiplying every per capita demand in African countries and India and so on by 5 or 20 or 10. But I mean, if some small degree of that occurs, that still spells a relatively strong growth trajectory for countries in which the per capita figures for plastics, especially as where it's more acute, are really in the kind of single-digit kilogram figures according to the data we have. I mean, we would definitely like to have a look at some of the figures you're talking about for some of the more detailed case studies, because, I mean, again, we find in the public sector, in the public realm, data on detailed stuff like this about yields of crops from particular fertilizers. We have a good relationship with the International Fertilizer Association, who have kindly supported us analytically through various aspects of data gathering and so on. But I mean, the public realm data for this topic is very hard for us to get high resolution data to do some of the things that Katherine mentioned that would be great to look at. Price sensitivity and elasticities and so on. But I think that chart for sure is at a high level. It's meant to drill home the kind of wider potential if even some of that equalizing in per capita demand came to fruition. Thanks.
Thanks, Peter. I am conscious of the time, so I think maybe we'll just end with one final question, Peter. If you were to do a part deux of this report, are there any topics that you think merit further research, understanding, of course, the myriad data limitations that we're dealing with? What didn't make the cut here that you think is still interesting to look at?
Well, I would definitely like to do more on this topic personally. It's a great interest of mine, and I think for several analysts at the agency. So we're definitely primed if there's appetite for it. The reception for this publication will certainly be a big factor in whether that comes about. But I think some of the aspects that we've touched on in the discussion are really where I think the most interesting aspects for further, more detailed analysis lie. Data pending and all of those caveats. But I think we made some good steps forward, at least in the public domain, for data, the link between end-use consumer products and the plastic and petrochemical products that we use and the impact on oil demand. I think we drew some nice links there, both physically and in the dynamics front, on the feedstock front. But we could go a lot more high resolution on that front. I think a lot of the kind of more detailed case studies outside plastics as well, fiber, rubber, fertilizers in more detail would be great to look at on the more consumption end and do a kind of full bottom-up analysis of those consumption drivers in even more detail would be great to do. And I think, I'm not sure whether this would be in the remit of the IEA, but I think one of the key drivers that I envisage being on the environmental side is the plastic waste leakage issue. I think is really garnering attention and capturing hearts and minds, and I think the extent to which that can kind of action behavioural change on the littering front and waste management front, I think is an area that would be great to study and see how we can galvanise the support that's obviously there in lots of communities. So the kind of behavioural links on that front would be really interesting to analyse, I think.
Great. Well, thank you so much for joining us. Peter is straight off a plane from Paris, so now I hope we'll have a well-deserved dinner and a night of rest. And thank you all for joining us as well. I just want to remind you that the full video recording of this event will be available on the website and on our website in a few days. And our podcast is something you can also subscribe to on iTunes and a number of other platforms I haven't even heard of, like Stitcher and SoundCloud, that make me feel a bit old. I also just wanted to highlight a couple of great events that we have coming up. One is on October 19th in the morning here on campus, the impact of U.S. LNG on Russian natural gas export policy. We're pleased to be joined by one of our CGEP fellows, Dr. Tatiana Mitrova, who's also the director of the Skolkovo Energy Center in Moscow, as well as a number of other panelists who will be joining her on that topic. And then on October 26th, the IEA will be back talking about their renewable energy market report for 2018, and the speaker will be Jaime Bahar, who is a renewable expert at the IEA. So please keep those dates in mind, and we look forward to seeing you again soon. Thank you all so much for coming.